Here is a handy table that lists the salient features of the transfer functions of the three basic converters. So if you have an ideal converter, or if the losses are not significant, you can use this table to quickly get the transfer functions of the basic converters. So what I would say here is that in each case the GVG, or line to output transfer function, can be written in this form with two poles and a DC gain. GVD, the control to output transfer function, will have the same two poles, it'll have a different DC gain, and it may have a right half plane 0. In the case of the boost and the buck boost converters, we have a right half plane 0, and in the buck converter we don't. This table can also be used for isolated converters containing transformers that are based or derived from these buck boost or buck boost converters. So for example, if we have a forward converter, we can use the buck transfer functions, and all we need to do though is include a turns ratio in GVG, which is the transformer turns ratio. And as far as GVD is concerned, the gain is actually written in terms of the output voltage V rather than the input voltage VG. And so the effect of the turns ratio cancels out, and you can apply this GVD transfer function with these coefficients directly. If the converter has inductors on the primary side, then you would have to reflect the inductors through the turns ratio of the transformer. This is the physical turns ratio in, before applying these formulas. Now, we've seen right half plane zeros arise in the buck and the buck boost converters, and they arise in other converters as well. And what I'd like to do now is briefly discuss where the right half plane 0 comes from and what its nature is. It actually causes some serious problems in the dynamics of the converter that make it difficult to control. So one way to view the right half plane 0 is this: that at low frequency the 1 dominates over the S over omega naught term, and so the transfer function is 1, which is positive. On the other hand, at high frequency, where S over omega 0 has magnitude substantially greater than 1, then this term dominates, and there's a minus sign involved. So at high frequency, we have a phase reversal from the minus sign. In a block diagram form, one way to view this transfer function is that we have a low frequency path this way that has a gain of +1, whereas at high frequency this path dominates, and it has the S over omega Z term, and it has the minus sign right there. So one interpretation of this from the frequency domain is that initially for high frequencies the transient response goes the wrong direction because of the minus sign. And then later, when the low frequency gain becomes significant, the phase becomes correct with the plus sign, and the output will follow the input. So one way to think about this then is, suppose that our input signal to our converter is some kind of step. Say we start at a low value and we step up to a larger value. So that's our input. And we would hope that the output would follow the input. Perhaps there's some transient response that has some lag and takes some time to get there, but we would like the output to eventually rise and follow the input. But the right half plane 0 response, the characteristic is that the output goes initially the wrong direction. So the output goes down instead of up. And then eventually, after some substantial time, it catches up and goes the right way and follows the input. So why do the boost converter and the buck boost converter exhibit this kind of behavior? Well, it really comes out of how the switching occurs to connect the inductor to the output. In each of these converters, the current that drives the output coming out of the converter is a diode current. And the diode conducts when the transistor is off. In fact, we can write the equation for the average value of the diode current, and it is d prime times the inductor current. So the inductor current flows through the switch to the output during the d prime interval. And this is true in both the buck and the buck-boost converters. So let's consider a transient where we turn up the duty cycle. Here are some waveforms. So this is our inductor current, including its ripple. It's operating here initially with D of 0.4. And we're switching, so we get some switching ripple like you see here. The diode current is equal to the inductor current when the diode is on, and it's equal to 0 when the diode is off. So here's a sketch of that, the diode current waveform, and its average, which is d prime times IL, is also illustrated here. Finally, I've illustrated the output voltage as well. So at this point right here, we turn the duty cycle up from 0.4 to 0.6. And we would expect the boost converter, with a larger duty cycle, would make a larger output voltage, and so the output voltage should rise. But what happens to the average diode current? It takes time for the inductor current to change, and right after we change to D equals 0.6, the inductor current hasn't had time to change much. It's a continuous waveform. So the inductor current goes through some transient, and eventually it builds up to a large value, but initially it hasn't had time to do that. On the other hand, when we change the duty cycle from 0.4 to 0.6, at this instant, the duty cycle immediately goes down. So see what happens to the diode current. The width of the d prime interval is less, and the average diode current immediately jumps down. Well, if you drive the output with less current, then the load can discharge the output capacitor and make the output voltage go down. So you'll see the output voltage initially dip. After some time, the inductor current builds up to a big value. And in fact, in steady state, the inductor current goes like Vg over d prime squared r. So with a square, the inductor current will build up to a much larger value. And we see eventually that the average diode current builds up to a value where the average is greater than it was before, even though the d prime interval is shorter. And so with this larger current, we have more current coming out of the converter that can charge the output capacitor up to a higher voltage, and eventually we come into steady state with a higher output voltage. But initially the voltage goes down instead of up. And so this part of the response is indicative of a right half plane zero. Now imagine the effect of this on a feedback loop. We build a control system for our converter that is trying to regulate the output voltage to follow some reference. When the feedback loop sees the output voltage go down, or if the output voltage is less than the reference, then the feedback loop will turn up the duty cycle. So what do you suppose will happen? If we have a wide bandwidth or fast feedback loop, it will see the voltage sag, and it will say, uh-oh, the voltage is going down, I need to turn up the duty cycle even more. So it'll turn up the duty cycle again to a larger value, which will make the output sag even more. And in fact, this can be unstable, where the converter will just hit the stops at D equals 1, and the output voltage will go to a low value. It can also cause the feedback loop to oscillate. One way to avoid this is to make our feedback loop slow so that it never even sees the sag. We make the feedback loop change the duty cycle only very slowly, and so it may not even notice the output voltage has gone down or even see anything until we get out here at a later time where the effect of the right half plane zero is gone. So boost converters, buck boost converters, and other converters that have right half plane zeros are notoriously difficult to control. And in fact, before these average models were developed, people didn't understand why, but they did know that boost converters and buck boost converters tended to oscillate, and they were difficult to control. And it was one of the early I think, victories of averaged converter modeling to be able to predict the right half plane zero and show why these things were happening.